Hello, welcome to our semiconductor education program. I'm Vincent Chang. In this video, I'm going to teach you how to solve input offset voltage of differential BJT differential amplifier. Before we move on, I want to make sure, you need to make sure that you got the previous video centered around the issue, why the concept of input offset voltage of the differential amplifier, why the formula is defined this way. So if you don't, you have to go back to the concept of input offset voltage of the differential amplifier. Personally, I think follow through the calculation part is easy, but get the concept and the understanding and the why is tougher. So make sure you get the concept. Input offset voltage of the differential amplifier. The right-hand side shows the differential amplifier. What's the first step? Grounded. When you faced, someone asks you to solve, to calculate, to analyze the input offset voltage, first step is grounded. And then DC ground, right? And then get the DC output offset voltage. Try to get the DC output offset voltage under a certain mismatch condition. The first offset, the first condition, let's say load mismatch. Transistor is matched, but load, external load, the collector resistance are mismatched. Let's assume the left-hand side up a little bit, and right-hand side collector resistance on the right-hand side down a little bit. So there's a variation. The difference between the two collector resistances is delta RC. Because the common emitter and then the DC-VB matched are equal. So current 50%, 50-50 split. From emitter to collector times alpha. And then you get the voltage on the left foot and output voltage on the right foot, VC2 and the VC1. Then you try to get the differential output. Right deduct left. VC2 deduct VC1. VCC got canceled out. RC got canceled out. Now there's only one item left, the delta RC item. First step, ground, input grounded. Second step, DC output offset voltage. What's the third one? Then you learn from concept video. What's the third step? The differential gain. The differential gain. So then you have to go back, therefore you have to go back, call back the small signal analysis, the differential gain. What is the differential gain? Now the one on the numerator is the DC output offset voltage. The one on the denominator is the differential gain. What is the differential gain? It's here. Remember GM times RC. Total collector resistance on the top and total emitter resistance on the bottom. And alpha divided by RE equals GM, transconductance. But what is the transconductance? In this situation, you cannot just put on GM. So what is the GM? Who decides the GM? Who decides GM? Bias and what? And temperature. So bias, what is the bias? Collector bias. Alpha IQ divided by 2. IQ represents the constant current from the current source. Temperature, thermal voltage. Then here's the outcome. Thermal voltage times the fractional change of the collector resistance, the fractional change, delta RC divided by RC. The second situation, let's assume the collector resistance is matched, but only focus on transistor mismatch. The second reason cause the offset voltage could be the transistor mismatch. Let's assume, because if you have a little bit knowledge around the semiconductor device, you should know the saturation current of the BJT is proportional to the emitter-base junction area of the BJT. Let me say that again. The IS, the saturation current, is proportional to the emitter-base junction area of the device. But during the integrated circuit fabrication, so the area might misalign a little bit, maybe mismatch a little bit. That causes the saturation current will be mismatched. So let's assume the Q1, the left-hand side transistor, make a little bit larger, and the right-hand side make a little bit smaller. The size is a little bit smaller. I'm talking about the size means, what I mean by the size is the emitter-base junction of the device. Therefore, the IS will up a little bit, and right-hand side will down a little bit. The difference, let's assume, is the delta IS. A split half, use the positive sign on the left, and down, and use the negative sign on the right. The total difference is delta IS. So now, in this situation, you can just simply put down the current, because the IS is proportional to the current. So which side the current is larger? By instinct, the left-hand side should be larger, right? By what? By how much? By the fractional change. Then the right-hand side will be lower. But you might be wondering, Vincent, what's this? Why is this? Where is the 2? I can understand IQ over 2. But why is the another 2? Delta IS over 2IS. Why not just, if you have doubt around this equation, if I move too fast, then I step back. Maybe let's go back. Probably you are thinking about this, right? So let's go back to the original. Should be IS1 exponential VB divided by 2VB are the same. So IS is different. So IS1. So what is IS1? So you plug in IS plus delta IS divided by 2. So this delta IS divided by 2. So you plug in the IS1. And then what? You can pull out the IS term. You can pull out the IS, so IS, and then 1 plus, in the denominator, 2IS. Is this. Make sense? So the first item is the half IQ. The ideal half IQ. IS exponential VB divided by VT. So by the same token, the current on the right-hand side should be expressed in a similar way. Therefore, if you get the 2 emitter current, it's very easy. Then it's your job. Try to get the 2 collector current. And then you have the 2 collector voltage. I'm going to skip the 3 steps and then jump to the final one. This is the answer. So very similar. The pattern is very, very similar. So this output offset voltage is created is because it's generated by the second offset issue, transistor mismatch. So also I skipped 1 step, all right? So you should go back, and what's the third step? VO divided by the gain. So you just pull the gain, GMRC back, and plug in the transconductance in terms of bias current and thermal voltage, you will get this. Takeaway. So 2 issues. The second issue is transistor mismatch, size mismatch, transistor mismatch. So proportional to thermal voltage and proportional to the IS, the fractional change of IS, saturation current. Same thing with the first issue, load mismatch. For the load mismatch, RC mismatch, then same thing. It's a beautiful outcome. Proportional to thermal voltage and proportional to fractional change of the collector resistance. This is the takeaway, right? So just remember, proportional to thermal voltage and proportional to fractional change, either from collector resistance variation, and also IS variation. We have come to the end of this lecture video. I hope you learned something from this lecture video. Thanks for watching.